In this video, we will see how to design FIR filter using windowing technique with the help of one example. So as given here in the question, design a fourth order low pass filter using rectangular window for the desired frequency response of low pass filter by WC equal to pi by 4 radian. Find the filter coefficient Hn. So from the given question, we have to first note down what all the information is given there. So as it is a fourth order low pass filter, so number of coefficients are 5 because number of coefficients are 1 higher than the order of the filter. Now we need to find the filter coefficient Hn, and where small n will vary from 0 to 4 because we need to find 5 coefficients of filter to fulfill the requirement of fourth order. Now the cutoff frequency for the filter is pi by 4 radian, and the given frequency is in digital because the unit itself is given in radian. So with this information, very first we'll try to draw it graphically, and afterwards we'll interpret this in the form of mathematical equation. So in the graphically, if we want to draw in the form of filter characteristic, where omega is a x-axis and h omega is a filter response, which is a consist of magnitude response here basically. So we can see here the complete range for omega is from minus pi to pi, and the filter is having low pass, which means to say all the lower frequency from 0 till pi by 4 has to be passed. So the cutoff frequency is pi by 4, that is minus pi by 4 and plus pi by 4. Till that, the response of the system is unity, means it is to design a low pass filter. From pi by 4 to pi, the response is nothing, that is a higher frequency we are not passing. So the magnitude at this particular range is 0. And similarly, from minus pi to minus pi by 4, also the magnitude is 0 because it is all higher frequency which we are stopping to fulfill the requirement of designing of low pass filter. The same information can be interpreted in mathematical way, that is Hd e power j omega equal to e power minus j omega tau, and where tau indicates the number of delay, and the delay value equal to m minus 1 by 2, where capital M is filter coefficient, and the value assigned here is 5. So tau value has come from here is 2, that is number of delays. And the magnitude information here is 1, and the phase information is depicted by e power minus j omega tau. And this is the information which is in the range of minus omega c to omega c. It means to say between minus pi by 4 to pi by 4 frequency range, the complete response of the filter is indicated by 1 into e power minus j omega tau, and remaining rest of the frequency, that is minus pi to minus omega c, the amplitude is 0. So that is the reason 0 is being marked. And on the other side, from omega c till pi, the value is again marked as 0. So it is mathematical representation of the given question. And now we need to focus on how to find the filter coefficient Hn. As we can see from the given information, the information given here is in frequency domain, and what is being asked in the question is Hn, that is time domain information of the filter. So very first step is to convert a frequency domain information into a time domain information, and for that we are using the concept of inverse Fourier transform. So with the help of inverse Fourier transform, which is used to convert a frequency domain quantity into a time domain, so Hdn is equal to 1 upon 2 pi Hd e power j omega, which is already written here, into e power j omega n into d omega. Hd into e power j omega is the information given to us. But before to substitute the value, we'll simplify this particular integration and we'll reach to this particular form, that is Hdn is equal to sine of omega c n minus tau upon pi n minus tau. Now all of us, we can see the input given here is omega c, and what we are obtained from here is Hdn, that is time domain information of the filter or filter coefficient. In this particular equation, omega c is a cutoff frequency which is pi by 4 given according to the question. Small n is a variable which is varying from 0 till 4, 0, 1, 2, 3, and 4. For 5 coefficients, this value of small n is valid here. And tau value is given here, that is tau is equal to m minus 1 by 2, which is 2. So all the information to obtained HDN is given to us. So we'll be solving this and we'll be calculating the coefficient of HDN for 5 different values of small n. So we'll proceed further and we'll be substituting in this particular equation very first small n equal to 0. So then equation becomes HD0 is equal to sine of omega c value given in the question is cutoff frequency, that is pi by 4, and small n is 0 and the tau given here again is 2 upon pi into small n is 0 and then tau value is 2. If you simplify this particular equation, it is sine of minus pi by 2 upon minus 2 pi. We all know sine of minus theta is minus sine theta, and denominator also having minus 2 pi, so minus minus will get cancelled and we left with the value of sine of pi by 2 upon 2 pi, which is again further can be simplified and the value is coming as 0.159. This is the filter coefficient at n is equal to 0. We will proceed further and we'll be reaching for filter coefficient when n is equal to 1, small n equal to 1. So HD1, again we'll be substituting in this equation HDN, that is sine of omega c, n is small, n is equal to 1. So 1 minus tau upon pi, 1 minus tau. If you simplify further, this equation is reaching to sine of pi by 4 by pi, that is 1 upon root 2 pi, and you can simplify and you can look into the value that is 0.225. Now we will be looking for the third coefficient of filter, that is HDN, and at the time when small n and tau they both are same, this equation doesn't hold good because of the special case of 0 by 0, which has to further simplify and using L'Hospital rule. And at the time when small n equal to tau, that is small n is equal to 2 equal to tau, that is 2, then we have to apply L'Hospital and the filter coefficient HD2 equal to omega c by pi. And omega c value is given here is pi by 4. Pi by 4 by pi, the value is reaching to 0.25. This way we could reach to the third filter coefficient, that is HD2. Now we'll be moving to the fourth filter coefficient, that is HD3, when small n value is equal to 3, and we again further simplified and we'll be reaching to the value of 0.225 while substituting the small n value as a 3 here. And the last fifth coefficient for HD4 for a small n value of 4, sine of omega c 4 minus 2 upon pi 4 minus 2, and will be reaching to the value of 0.5159. This all is the filter coefficient which we could found with the help of inverse Fourier transform. Now we will be moving to the windowing technique, and before that we'll see FIR filter having a property of symmetry and antisymmetry using this equation. If the filter coefficient is fulfilling the requirement of Hn equal to H of capital M minus 1 minus n, where capital M is a filter coefficient length and small n is a variable, and if they are fulfilling the requirements such that H is that, 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 H is